and I'd quickly like to invite our next two speakers who are going to have a chat. We have Dom Robinson, our founder, who most of you should know by now, and Ian Nock, a colleague of mine for well over 10 years in multiple places. And they are going to take the floor and get us into this story of what power factor is. Over to you, Dom.
I noticed you relocated very quickly there, Ian, from Costa to the IET.
I have multiple personality disorder when it comes to webinar software and things, and obviously I was in a completely different setup before, which actually is that's actually a Starbucks. I quite liked it that period because it was raining like hell outside.
Perfect. So listen, thanks to Ben for handing the floor to us, and thanks to Hemini and Mike, and a very lively and interesting presentation from Barbara as well, which I really enjoyed. So those of you that know us will know that Ian and I want to go a little technically deep, so we just raise that flag up front here, and if you get a bit lost, say so in the chat room or in the Q&A, and we'll slow down and back up a little bit, but we are going to sort of let ourselves off the chains and go for a little bit on a reasonably technical subject. Just to give first a quick couple of words of introduction. So yeah, as Ben mentioned, I founded Greening and Streaming several years ago, and with some delight handed the reins to a much better leader in Ben. And so I still look after our working group 1, which is our language lab, where we look at, in some pedantic detail, we look at terms and measures that we use in sustainability and in the engineering of streaming and broadcast. As those two worlds collide, there's been a tendency to talk across purposes about certain terms and hand wave and glibly comment on the effects of things without really deep understanding, and that's something that I feel strongly is foundational to being able to make good decisions about engineering towards better sustainability. So that's my introduction. Ian, do you want to say a few words of introduction yourself, and then I'll introduce the topic?
Yes, yeah, of course. So my name is Ian Nock, of course, and essentially I'm the managing consultant of a small consulting company working in the technology and product area for a variety of different clients, you know, the operators, technology providers, etc. But also I work with the Institution of Engineering Technology, which is the largest UK institution representing the professional engineers working across many fields, one of which includes things like media and broadband and telecommunications. And in that area, I'm the vice chair of the committee that actually manages a variety of different events that we put out to the whole industry as a whole at various places, both through our YouTube channels and also in-person events, particularly at places like IBC, like we have later on this year. And that's what we do. But also as part of that, the Institution of Engineering Technology is also one of the owners of IBC, and through that we take part in the IBC accelerators as a champion, and also sometimes as a pseudo vendor, helping out where we can, because it's important to the IET in terms of its 2030 strategy to ensure a sustainable and better world in which to live, basically. So that's really where we are, and obviously I've been working in a variety of sustainability technology aspects, trying to keep people honest about what the technology really is doing, because I think that's important, that people need to do that. And I think that's done where you and I have a great fun, because you raise a question, I'll give an answer, where someone else says something's good, I'll point out where it's bad, and where some people say it's bad, I'll point out where it's good, all based on the facts. In fact, just the facts is what I try to achieve.
Yeah, absolutely, and I think we can be sticklers for rigor, and I think that science is a process of testing things to predict the future until you're not getting them wrong, really, and that's a discipline which sometimes gets forgotten. So let me just set the scene briefly. At Greening and Streaming, we have looked at a number of reports, and I've noticed that there's some questions from Alethea in the chat room, and I'll share some links in a little bit to some of the reports that have historically been shared over the years. Universally, as we read these as a group within streaming, within Greening Streaming, and then as we discussed them with wider communities such as Ian's, we raised a few eyebrows. There was, the early and key association, which still persists as a myth today, is that there is a linear relationship between use and energy, so that if you consume more television, you somehow consume more energy. And while that seems like a logical thing to do and is often done with great intent because of the desire to create circularity and make consumers involved in the decisions, there are many aspects of the base load of the providing the availability of service that do not respond in a linear way. They respond in a quantitative way that tends to be measured in next rollout or next architectural change rather than in the actual use of those technologies. And as we've dug into that area, we've discovered that it's not just about measuring the energy of something that's going on in the network. It's also a question of where you're measuring that energy, and that was something that Ian started to raise at a number of discussions. And the fine, sharp edge of that conversation is really has really boiled down in a bunch of our language lab discussions to a discussion about something called power factor. So at a high level, what's power factor? What if I told you that a device showing 2 watts of consumption actually requires 20 watts to be generated? So your accuracy about reducing your 2 watts to 1.7 watts as you change the power of your codec, or your TV goes from running showing 80 watts to actually requiring 300 watts of power to be generated. What's going on? And when we make impacts on those last inch measurements, are they actually really having bearing upstream? So we've probably confused you with that opener. Let's go back half a step and actually try to understand what power factor is, and that's really where Ian is the supremo. So Ian, can I hand the floor to you to give us a little bit of a primer?
Yeah, so this is where it gets awkward, because power factor loses in the game of trying to create an explanation that works with a 5-year-old, which is who we all are in reality when we're learning new concepts. And it's really hard to explain because it's, in many respects, it's very counterintuitive to the way you think about way things work. But it comes down to just basically how fundamentally we generate electricity and how we distribute it and how we consume it. And I'm just going to share something on screen right now, if you give me a second. So I prepared some slides that will help in the conversation, and not too many, don't worry. So the basic thing we've got at the moment is I'm going to scare you with some diagrams first, mainly because I think we just need to make sure people know what alternating current is. It's weird, but some people don't really grasp fully what it is. And what you got shown on the screen now is alternating current is literally where we supply electrical current that actually varies over time. Normally in the UK, it's 1/50 of a second for the period of one of these variations. So we get 50, and I prefer, actually it's interesting, we have a power supplied at 50 hertz in Europe. 50 hertz obscures really what's happening. The old way of describing it works better. It's 50 cycles per second. So the current basically changes to plus and down to minus again 50 times a second to supply the current to everything out there for your lights, for your cooker, whatever. And the way it supplies that current is it also supplies it supplies it in the context of a particular voltage that tries to be stable. I say 250 volts, 240 volts, as you say. And the whole point is that the power generators and distributors then manage that balance between how much current is needed to supply the power in a network. And that's what you see on screen now, is the way the current varies. I'm just going to show a little bit of an interesting point here about the power. The power is actually really is the multiplication of the voltage and the current together. And you'll see here I've shown the power is shown in a deeper red with this dotted line here. And you'll see it always stays positive on this particular one because you've got voltage and current varying plus and minus all the way along that line there. And it generates a positive power, which is shown in these 2 blips here. And everything's really nice with that, really nice. However, reality hits in that the balance between the the current and the voltage will go out of phase based upon what you've got connected to the electricity supply. And that's both on an individual device basis and effectively the whole network. And what that means is you end up with this, which is what's shown on screen. It's a really complicated diagram, which is showing that the actual amount of power from the same amount of current and voltage as shown in the other charts, the actual power created is actually lower, being shown here in the dotted line, shown here just for 0.8 there, and here it's gone up to 1, and same on the other parts of this, that it goes up and down in a very negative way. Now, that is the actual technical way of visualizing it, but a much better way of visualizing it is as beer. And what this really is, always better. And you can think of the fact that the real power needed by your device plugged in is shown here. It's the beer part, not the head. It's the beer. The amount of power generated to supply that real power is the apparent power. And the difference between the two is the head of the beer, which is the reactive power. And it's that proportion of the power that's out of phase, or the way that the current and the voltage is out of phase. And so you end up with this thing where you're generating more power at source to be consumed at the same level on the end device. So if you've got, say, a power factor of 0.9, which I'll come to what that means in a minute, that means 0.1 of the overall power is actually in the head, and 0.9 is of the power is in the body of the beer. And that only becomes really, really, really noticeable when you realize that power factor in our real life networks tries to be as close to 1 as possible. So we try to have the real power be as close to the apparent power as possible based on our designs of all the devices and components and systems that connected to our power distribution. However, that doesn't always work out. And what it makes a big difference on is if you look here where we've got a very much lower power factor, it has a much bigger head, a much smaller body of the beer. And in effect, therefore, you've got to think about it as the fact that you need to drink a pint of beer, therefore, you need to drink a lot more pints of beer, is probably the good takeaway from this. Because you've got a wasted head that's there, that's just in the system, it's lost to you. And if you want to drink a whole pint, then you need to actually, in this case, you have a lot more than 1 pint of beer to get that in your body. And it really comes down to that, thinking about that concept that that's how power works. And power factor is the ratio of the real power to the apparent power. And why that's important comes about in what Dom has just mentioned about the fact that why do some devices need 20 watts generated when they only consume 2 watts? And it comes down to the fact of why the voltage and current goes out of phase with each other. And that's down to the fact that every device has a different load characteristic on the way current and voltage is actually, the way that current is consumed to transfer into power, used, work done, basically, on the device itself. And sometimes it leads, the current leads the voltage, i.e. it's ahead of it, and other times it's behind it. And it all depends on whether the device is and this is where I take you back to your high school physics, maybe, and that is where you have capacitive loads or inductive loads. And a good example of a inductive load is one you know all yourself, in that if you have an electric cooker, that is an inductive load. If you have a washing machine, that's an inductive load. What's a good example of a capacitive load? Well, actually, pretty much all electronic devices which use a switch mode power supply. So they are actually making sure that when you supply constant voltage, which is 240 volts in the UK, that 240 volts, or 230 volts technically, is maintained by the power distributor. They need to achieve the work done for the load, so they need to vary the current supplied. And that's where they control. They control the amount of current generated. And power generators and distributors are constantly balancing the entire system that is the power distribution network to ensure that you've always got 240 volts or 230 volts in your home, and that all the current you ask for is always provided when you want it, whether it's out of phase or in phase with the voltage. It's always there trying to maintain it. Otherwise, you would have your system brownout, as it's lovingly called, which goes from the fact that it will not have enough current there to actually keep it running. So there's a lot of work being done by power generators to do that, and why it's suddenly super critical to that 2 watt and 20 watt thing is because of the nature of modern equipment with these modern switch mode power supplies. We do have an awful lot of power supplies that operate with a sub 0.9 power factor, as low as 0.1. In fact, it varies. It can vary depending upon what it's actually doing at that point. So the standby discussion, all the standby devices that I've actually measured in my home and in my home lab, I should say, they're all basically very low power factors of 0.1, 0.15, 0.2. And in general,
so actually putting the message is sometimes putting something on standby in a 0.01 power factor environment might actually mean that the 0.2 watts of standby is actually using more than the 15 watts or 10 watts that you might be using at full load. So suddenly, when you can't, unless you're understanding what's going on in the grid, you simply would argue, oh, well, I'm using less energy. But that's not strictly true, because you might be creating more demand for energy in order to rectify the power factor.
In fact, that was a very specific one. I know of a set-top box that in general usage uses 3 watts. And you place the box, the standby, it uses 0.5 watts. But its power factor of 0.5 watts is 0.1. So actually it's requiring the generation of 5 watts. Or generating the current to provide that 0.5 watts, but overall it's 5 watts of power being generated, which is more than the active mode. But
so
it's not,
we got sorry, carry on.
but it's of course in all these things, it's more complicated than that, because at the end of the day, it's all about the flow of current. And another analogy, and I did advertise this as being a wonderful selection of imperfect analogies. You got to think about electrical current as like water, and you've got to supply enough water to keep a constant flow and the pressure required at all the endpoints. And if you don't supply enough water, then obviously things stop working. But once you supply enough water, it's got a certain amount of pressure. You can have your shower, you can have your washing machine can work things, and you've got to think of it as a flow. And when you have that flow, if you don't use that water, then it flows back in the system. But there are limitations in the way it can flow back. And because of the way that generation companies and distribution companies manage that flow, sometimes they manage that flow by just spilling it on the ground, effectively, to take the analogy.
Because that's exactly which is exactly what a heatsink does.
They
on a transformer.
put it to a large load and they burn it off in heat, and that's when they've done it bad.
And now, really, so that's going to provide a bit of a segue. We've got 2 or 3 themes we want to try and crash through in the next 5 or so minutes. So, so we've given some context as to a key inaccuracy in measurement, which should be reviewed and filtered back into almost all the climate science that relates to the end-to-end streaming ecosystem, because it's simply not even mentioned in any report I've ever read. Until the one which I'll drop into the chat room now for people to find, which is the very discussion that we're sort of promoting here. So if we go to, if I just drop this for everyone into the chat room, there's a link to Greening Streaming's publications page, and you'll see at the top of there our 5-page paper about power factor and streaming. But one of the key things that we should touch on while we're live on the webinar here is why streaming is uniquely vulnerable. Streaming spans everything. We've got data centers, networks, edge devices, consumer devices. We've got the full sort of gamut, and each stage has different power factor characteristics. Obviously, there's a lot of talk about AI and data centers and data center growth at the moment, so it would be remiss not to think about what's going on in the data center. But I think one of the conclusions that we came to in our research and our paper is data centers are big energy buyers. They make damn certain they don't waste money, and so actually commercially they're quite attuned to being efficient, their inefficiencies are in being over optimistic and making too much infrastructure available that's not being used. And so actually, if you look at the PUE of a data center, it's fairly analogous to a power factor measure, and most PUE measures of data centers are topping out near between zero point 0.9 and almost perfect efficiency. They are really quite optimized environments. But as you mentioned a minute ago, there are so many different interconnected systems. And we looked at Romain's results as he'd looked at base loads in routers, and they're sitting at about 85% utilization. So that means that the use from nothing to everything on the router varies their power by 10 to 15%. But at the same time, that their power factor varied from 0.9 to 0.4. I can't remember the exact number, but certainly through a load-based power factor variation. And so, again, this really reinforces the non-linearity of the relationship between use and carbon footprint that ultimately derives from energy. I just wanted to, I wanted to sort of contextualize that for greening and streaming, that there is a big question about what's going on across these disaggregated large infrastructures and how you can start to account for power factor in that complex environment.
Yeah, and this is where I have some good news. Historically, big, large business users like data centers for cloud infrastructure, they actually, like all business consumers of electricity, they actually get charged for the reactive power, the additional power, that power. So if they have an unbalanced network, which has an overall power factor of less than 0.9, they are generally getting charged at a slightly different rate in monetary terms for that power that is being used by, but the end result of them actually calling off and requiring more power to be generated for the load that they have. So they actually do expend money in power factor correction. And it's an important point to know as well, this conversation about power factor applies to AC current. And of course, that's another thing that a lot of data centers do, is they convert to DC power as quickly as possible, and that they actually drive a lot of their infrastructure from DC, because once it's in the data center, that's an easier way of handling it. And you can also focus on making the power supply as efficient as possible, both from a power factor perspective and from a losses perspective. And therefore, they spend money on that power factor correction of that infrastructure, and that's really great. But the reason I draw out the attention about what happens for the actual device itself is where you've got your infrastructure outside of a data center, like in someone's home, consumers don't get charged. It's actually very much a power distributor responsibility to balance that network. And whether we've got inefficient devices that have low power factors, or whether we've got efficient devices with high power factors, that's basically effectively a little bit of a Wild West. There is a drive in standards to ensure when you're making large uses of current for larger devices like washing machines, then you should have power factor correction. But in the consumer environment, that's not generally applied.
It's not applied.
Not applied. And I think the question mark here is how effective is power factor correction, and what do you do about it? Well, better quality power supply with built-in power factor correction would improve things, even if it's only a small amount, simply down to the multiplication factor that we're here talking about. Millions of homes which have equipment in them are running inefficiently. And it's important to know that you mentioned PUE, and we also mentioned standards. Now, there is some reference to power factor in a lot of these standards, but only from we just need to be aware of it, rather than actually managing it. And they're not taken into account in any of the end standards and PU calculations. It is not included in the losses, and that's what to think about.
And what concerns me is that there's pressure for CSRD, there's pressure for other regulatory frameworks to start to assess the energy consumption of digital media groups, digital media platforms and technologies and so on. But we don't have these foundational numbers, right? We have policymakers don't understand the physics, and there's a big regulatory blind spot. Watts per stream is fundamentally meaningless anyway, and it's even more meaningless and possibly out by factors of orders of magnitude without accounting for power factor. So anyone who's relying on anyone's carbon calculator today is using something that's fundamentally wrong. So I think Ian's having a camera moment here.
Yeah, I'm having a camera glitch.
That's okay. There we go. Cool. Oh, that's much better. Let's just last sort of couple of minutes. Let's talk about the scale of the problem and also maybe a few last thoughts about what we can do. Obviously, Kemeny mentioned and Ben were talking about the consumer device multiplication issue. Clearly, consumer electronics has little regulation over power factor in these little throwaway power supplies that get dropped out with every device. I liked your comment earlier when we were talking this morning about having USB power supplies in your wall sockets and doing the step down conversion, so you haven't got hundreds of inefficient power factor based devices. Maybe you have one high quality device at the hub of the home, which then delivers DC around the home. Are those the sort of ways that we can really attack the scaled out problem, or are there other strategies that come to mind?
There can be. There's the world of electrical supply is actually filled with this discussion on what's best, DC or AC. AC won out primarily because it's got an efficient way of distributing the electricity over large distances. Otherwise, all of us would have a power station within 150 meters of where we live, which is not probably a great thing, especially if it's belching out smoke, if it's the old style power stations. If I was recently in Toronto, and there they do have power stations right in the middle of the city, which is quite interesting to see, but that's an historical thing. But that thing of, well, AC supply to the home, and then is there a move towards DC supplies being more commonly done within the home? Thus, they could apply power factor correction at that main conversion from AC to DC. That would certainly offer a lot of interesting possibilities. But of course, we have a massive infrastructure problem with that because we all have wires in our walls for AC supply. We don't have wires in our walls for DC supply. So at the moment, when I talked about us using USB power sockets, at the moment, every single one of those little power sockets has a little switch mode power supply or transformer contained within them, which is probably horrifically multiplying the issue rather than solving the issue. So, but it is actually, we have to raise that question, considering how many devices we have in the home now that are powered by USB or possibly powered, especially with the very latest 200 watt standards for USB-C. That should really obviously be thought about. But that's a long-term big decision to be had about how do we provide electricity within the home. And I think it would be good to actually make that discussion about, well, is it time that we make that switch back to DC for the consumer itself? And knowing that actually some AC supply is still required, because if you want to use very, very high power supplies, such as for an electric cooker or a EV charging station, then yes, those will still necessarily need that very high power, high current supply and have a very effective and efficient power factor correction in those. In fact, they do have them in EV chargers. It's a major part of their design, because they're going to have a large impact on the energy consumption of the home. I think there's just been an assumption that we don't have many devices or many things in the home that have these low power factor device characteristics, but actually we do. If you take it from 1970s, when pretty much we had a cooker, we had a television and a radio, to where we are today, where each of us have a tablet, a mobile phone, a laptop, computer at home, a router, mesh routers. The multiplication of complexity for that. So maybe there really is a need to look at, is it time to switch to DC in the home to solve this efficiency and effectiveness problem?
Yeah, absolutely, brilliant. Okay, so I think we've probably baffled some of the people all of the time, and all of the people some of the time, but hopefully we've got people thinking. I put a link to our paper about power factor into the chat room, so please feel free to grab a copy of that and get in touch with us if you want to get involved in the discussion. I think it's probably too early to be calling for kite marking on power supplies, but I think that's those are the sort of discussions that I would hope to see from the Consumer Tech Association, and indeed from the enterprise tech and the biz tech sort of environment. I think those are those will help people really understand what energy they are using and start to put evaluated comments about how much that really might translate into an environmental footprint in the long run.
And we have to give plaudits where plaudits is due. A lot of the standards, particularly from the EU, cover all of this, except for power factor.
Yeah, exactly.
So they are
Exactly.
efficient. They do focus on efficiency. They focus on ensuring that we're always advancing in the face of new developments in the industry. It's just that power factor is the thing where I think there's been a global decision to not worry about it so much on the small devices. But when we've got
Yeah,
millions of those small devices, that makes it a big number.
yeah, yeah, absolutely. Cool. Ben, are you out there? Have you got any Q&A for us?
I just had that question of, despite all the technical weeds and complexity, I think some of our people will have understood. A few dropped off, so it got too deep for them. But do we have any grasp, any notion of the scale of the problem? So power is being generated. It's not all being consumed. It's being lost. So two questions. One is, of the loss, Ian said some generators, distributors of power have means to recuperate some of that power factor loss. Others don't. Is it 1% that recuperate, 90%? Do we have any idea of that? And the other question is, do we have any idea of the scale of the problem? How many, are we talking sort of millions of gigawatts, or has anybody done any global scaling of
I
this,
think
how big the issue is?
I think in the power engineering circles, there's probably been a lot of discussion, but in the past, not necessarily in the present. I think there's probably active discussions in the operations of power distribution and generation, but based on the perspective of managing the issue that they have. And from their perspective, all they see is a widely varying load with adjustment in phase of current that they just manage. And if they misdo it, then they dump that load somewhere and we have some waste. But you see, this is the issue, is I can tell you now, if you're trying to do the mathematics of how much energy is generated and count all the losses all the way down the line to the end device, the key impact there is you won't end up with a calculation that balances. But if you actually take it back to how they're managing that power consumption, they're just accumulating as one mass, and how effective they are is just written into the reports of how effective they are at balancing current supply to power demand. That's where it fits. But the thing that's an absolute real loss all the time is if I've had to generate 20 watts to supply my 2 watts, I am generating 20 watts, and with losses in the distribution of that electricity from that 20 watts down to my home, I've always got that loss, even if eventually the current is supplied back and piped to somewhere else for use by another set of devices in effect. And that's a real loss. But the scale of that, again, it's who knows yet.
Okay.
Are we actually measuring that? That's hidden behind the boundaries of the power engineering world.
Well, thank you very much, gentlemen. That was
all.
enlightening, even for me, although I participated in a lot of the discussions, I still learned some more. And there's more to learn.